We have already seen the differential protection. So we have seen percentage bias protection also in the earlier classes. We are discussing about different types of relays. Okay, same concept here, but okay, only the difference is in while discussing about differential protection, we used only one winding, and we didn't mention what is the element that is to be protected there. Okay, so simply we said there, let us assume that this is a portion that is to be protected by differential protection scheme. Okay, so let us discuss differential protection of the alternator or merge price circulating current protection of the alternator stator windings. Okay, as I have shown you this, you can see here, this is the generator winding here, alternator winding, three-phase winding. So this is the schematic arrangement of the alternator windings. Stator windings, and to which we are providing the merge price protection here. So you can see here there are two sets of identical CTs on both sides of these three-phase windings, and the secondaries of these CTs are connected in star at one end. At one end, the secondaries of the CTs are connected in star, and their other ends are connected through pilot wires. Okay, the other ends on the secondaries of the secondaries of the CTs, other ends are connected through pilot wires. Okay, so other ends of the secondaries of CTs are connected through pilot wires, and one end of the secondaries are connected in star, and they are given to the neutral point, or they are grounded, you can say. Okay. So these wires which are connecting the relay coils to the transformer secondaries, these are the relay coils. Okay, to this transformer. Transformer means what here? It is the current transformer. Okay, transformer means it's not two winding transformer, it is the current transformer. These wires are known as pilot wires. Okay, so these relay coils R1, R2, R3 are connected in star. Okay, and their neutral point is connected to the common CT neutral point. Okay, this is the common CT neutral point. This point, you can let us assume this is a common CT neutral point. Okay, so one side is one side of this coils is relay coils is connected in star, and the star connected will definitely have a common neutral point. That neutral point is given to the common neutral point of your CTs. Okay, so common neutral point of the CTs is same as the neutral point of your star connected relay coils. Here the CTs on both sides of these windings are connected in star, as well as the relay coils are also connected in star. Okay, so you can see here the relay coils are connected between these pilot wires and the neutral point of the CTs. Okay, so now to provide equal burden on all the three CTs on both sides of this three-phase winding of your alternator, the relays must be connected across equipotential points on these pilot wires. Okay, so in order to provide equal burden on the all the three CTs on both sides of this three-phase winding, okay, the relays must be connected across equipotential point on these pilot wires. Okay, so equipotential point means it is the point at the center of this pilot, or the center point of this pilot wire is nothing but the equipotential point. Okay, so relays are always placed at the midpoint of this pilot wire. Okay, the relays are always placed at the midpoint of this pilot wire. So it is always convenient if we are unable to locate the midpoint of this pilot wires, then it is always convenient to place these relays R1, R2, R3 relays nearer to the CTs, okay, which are placed nearer to the main circuit breaker, okay. So whichever, if we are unable to determine the equipotential point, it's better to place the relays, okay, nearer to the CTs which are located nearby to the main circuit breaker. Okay, and in order to get the in order to, the main purpose of placing these relays at the midpoint of the pilot wires is that we want to equally distribute the burden on both the CTs. So in order to equally distribute the burden of both the CTs, if you are unable to determine the potential point on the pilot wires, then it is better to use the balancing resistors. Okay, it's better to use the balancing resistors. So this can be achieved by inserting the balancing resistors in series to the pilot wires here. Okay, to shift the equipotential point nearer to the main circuit breaker. Okay, so if we are placing this balancing resistors, it will shift the equipotential point nearer to the circuit breaker. Okay. So usually the resistance, balancing resistance that are used, they are adjustable resistances. Okay, so we can adjust the resistance value to get the exact balance between these two CTs. Now the relays that are used for the protection, okay, of this generator alternator windings, those relays are usually electromagnetic type relays, and they are instantaneous type, electromagnetic type instantaneous relays. So the main purpose of using instantaneous type electromagnetic relays is that the fault must be cleared as quickly as possible. Okay, so in order to clear the fault as quickly as possible, we are using electromagnetic type instantaneous relay now. So whenever we are using a protection system, and whenever we are discussing about a protection system for so and so equipment, there will be always two conditions. One condition is normal operating condition, another condition is the faulty condition. Okay, now let us initially discuss about the normal operating condition. So under normal operating condition, current at both ends, okay, both ends of these windings, okay, current at both ends of these windings will be equal. At both ends, this end and this end, the current will be equal. So the induced EMFs across the secondaries of these CTs, okay, the induced EMFs across the secondaries of these CTs will be equal. Okay, since the induced EMFs are equal, okay, so the differential current that has to flow through this relay will be equal to 0. Means no current will flow through the operating coils of these relays. Okay, so we have already discussed the concept of differential relays. Okay, so if I1 current is flowing from CT1 in the secondary and I2 current, if I1 is equal to I2, they will be equal and opposite. Then the current that is flowing through this relay will be equal to 0. Okay, so since the EMFs induced across the secondaries of these CTs are equal, definitely the currents flowing through the secondaries will be equal and opposite. Hence, the differential current flowing through these relays will be equal to 0. Hence, the relays will not operate and trip circuit will remain open. Okay, so this is the trip circuit, and this is the relay coil, and this is the moving contact. Okay, so if the relay coil is energized, moving contact will come in contact with these fixed contacts. These two are the fixed contacts. Okay, similarly about this and this. Okay, so now this is the normal operating condition. Under normal operating condition, the current measured by the primaries of these CTs will remain same. So on both ends of these windings of the alternator or generator. So therefore, the EMFs induced across the secondaries of the CTs will be equal. Hence, the currents that are flowing through the pilot wires will remain equal and opposite. Okay, in all these three phases. Therefore, the differential current that flows through this operating coil will be 0. No current will flow. They will. Okay, and relay remains inoperative. Okay, so now let us consider the next case, that is under faulty condition. So let us assume there is a phase-to-phase fault or phase-to-earth fault. Okay, LG fault or LL fault occurs in any of these findings. Okay, so if fault occurs, definitely the current measured by these primaries of the series on both ends of the windings will no longer will remain same. So if the currents measured by the CTs primaries is no longer same, then the EMFs induced across the secondaries of the CTs will no longer be same. So because of that induced EMF, current that is flowing through these pilot wires will no longer be same. So definitely differential current will flow through these relay coils and the trip circuit. Of course, even though differential current is flowing through the relay coils, okay, or relay circuit, if it that the differential current attains the reset value, okay, if it attains the reset value or if it attains the preset value, okay, not reset, it is preset. Okay, if it attains the preset value, then the relay coil is energized and hence the moving contact comes in contact with the flip circuit. Okay, so even though fault current is there, okay, differential current is flowing through this relay coil, if it won't reach the preset value, then the relay will not operate. Means for very low abnormal conditions, very low abnormal conditions which won't cause damage to the equipment. Okay, okay, so the relay will not operate. Okay, so the fault current due to which there are chances for the damage to the equipment which is to be protected, for such fault currents only the relay will operate. Okay, so the even though fault current is there in the relay coils, okay, the relay coil will be energized only when the fault current reaches the preset value. Okay, so if it reaches the preset value, definitely the current will flow through this operating coil, relay coil is energized and hence trip circuit is closed. Okay, now for more clarity, let us assume LG fault has occurred in phase R. Okay, in phase R, some fault has occurred, LG fault. Okay, so fault F has occurred. Okay, for let's assume at this some point F, LG fault has occurred, line to ground fault has occurred here. Okay, now so line to ground fault has occurred in phase R. So definitely the currents measured by these two CTs, CT1 and CT2 of this phase, the current measured by the primaries of these two CTs will no longer be same. So hence the EMFs induced in the across the secondaries of these two phases will no longer be same. Okay, so this current in this phase R will flow through the core of this generator and through the frame of this generator to the earth. Okay, through the core and the frame of the generator to the earth because of this LG fault. Okay, so since the currents in the primaries are no longer same, the induced EMFs across the secondaries of these two CTs will no longer be same. Hence, in this pilot wire, the differential, the currents I1 and I2 due to CT1 I1 and due to CT2 I2 currents will no longer be equal. So the differential current will flow through this relay coil R1. Okay, let us assume this as R1, R2 and R3. Okay, R1, I can write it. R1. So I will write it here. I will place it here. Okay, now, so because of because of the fault, LG fault that has occurred in phase R, okay, I1 current will flow in this secondary of this CT1 and I2 current. Okay, this difference of I1 and I2 will flow through this relay coil R1. Okay, if that fault current exceeds the preset value, this relay then this trip circuit is closed. Okay, and when the trip circuit is closed, what will happen? Circuit breaker will open. Okay, so this is it. Okay, so this is the operation of this. Okay, similarly, if fault occurs in between any of the phase and any in between any two phases, so let's assume some LL fault has occurred. So there is a short circuit between Y and B. Okay, if there is a short circuit between Y and B, definitely the currents measured by these two CTs on both sides will no longer be same, and hence what will happen? EMFs induced across the secondaries of these two cities will no longer be same. So differential current will flow through this relay coil, as well as through this relay coil. These two relay coils will be energized and trip circuit is closed. Okay, because of these two relay coils, and hence the circuit breaker is open. Okay, so this is the operation of your differential protection of your generator or mass price circulating current protection of the generator. So there are some limitations for this. Okay. So in order to understand the limitations, let me show the image. By looking at this, it will be more easy for you to understand. So limitation for this type of protection is that if LG fault occurs, okay, at the neutral point, this is the neutral point. Okay. So this is the neutral point. Let's for this generator windings. Okay. So if LG fault occurs at this neutral point of the generator, and if you see here, the neutral point has been earthed by an earthing resistance. Okay, so you can connect this neutral point to the ground. Okay, then you can use either earthing resistance or reactor or a transformer. But in practice, earthing resistance, I'm sorry, reactor is used very rarely, as well as a transformer winding can be used for grounding purpose here, but it is used only for large machines. So in general, earthing resistance will be used here for grounding the neutral. Okay. But in practice, it is observed that so if fault occurs near the neutral, then it is not possible to protect the stator windings from this fault current because of the earth fault at the neutral completely. Okay. So why? Because when earth fault takes place nearer the neutral, very small EMF will appear across the relay coils. Okay, so very small EMF means very small current will flow through the operating coils, because very small EMF will appear across the secondaries of these CTs, and because of that, very low current will flow through the relay coils. Okay, so when current is very low, if the current won't reach the preset value of the relay coil, even though fault has occurred nearer the neutral, these relay coils will not operate. Okay, and since we are connecting here an earthing resistance, okay, the current that is flowing through this operating coil will further reduce. Okay, it will reduce to a very low value. Okay, because of this earthing resistance. Okay, that's the drawback of this merge price protection. Okay, so in practice, because of this drawback, okay, so we are unable, we are able to protect the winding if LL or LG fault occurs either on any side. But if LG fault occurs at the neutral point, okay, the relay is unable to sense the fault, it is unable to operate. Okay, so we can say that this protection means is unable to completely protect this generator windings 100%. Means we are unable to provide 100% protection of the generator windings by this merged price circulating current protection method. Okay, so the protection that we are able to provide here is only around 80 to 85%. Okay, we are able to provide only to 80 to 85%, and remaining 20 to 15% of this generator winding is unprotected. Why? Because since the neutral is earthed here, very low current will go through the relay coils, even if LG fault occurs at the neutral. Okay, and if very low current is there in the relay coil, and if the relay is unable to sense the fault, then it is open use. Okay, means that fault may occur if the relay is unable to sense the fault, means it won't be able to operate the trip circuit and circuit breaker will not open. Okay, so merge price due to by this merge price circuit current protection scheme, we will be able to protect the alternator only 80 to 85%. Okay, so let us go for the next method of differential protection of this alternator. So it is a modified differential protection of alternator. Why? Because we have to overcome the limitation of the differential protection of the alternator. So that limitation has been overcome in this method of protection. Okay, so you can see the schematic diagram here. So similar to your previous case. Okay. So similar to your previous case, here in this case, also you can see the CTs on both sides of your alternator. On both sides you can see the CTs. Okay. So this here also the CTs are connected in star connection. If you see, the secondaries of the CTs are connected in star, and their neutral point is grounded here via this S1 and S2 pilot wire, and the other ends are connected. Okay, the secondaries of other ends are connected through pilot wires, and relays. Phase fault relays are there, two phase fault relays are there, and one earth fault relay is there, and one balancing resistor is there in this case. Okay, there is one balancing resistor, two phase fault relays, and one earth fault relay. Okay, that means that if earth fault occurs here, only this earth fault relay will operate. If phase fault occurs, PC and PA will operate. If earth fault occurs, ER will operate. Okay. So under normal operating condition, currents at the two currents at both the ends of the stator will be equal, meaning the currents in the primaries of the CTs for all these three phases will remain same. Okay, so when the currents in the primaries of the CTs under normal operating condition is same, definitely the EMFs induced across the secondaries, okay, EMFs that are induced across the secondaries will remain same. So the EMFs induced across the secondaries is same, means definitely the current that are flowing through the pilot wires due to the EMFs induced across the secondaries will be equal and opposite. Hence, no current will flow through this phase fault relay as well as this earth fault relay. Okay, so the relays remain inoperative, hence the trip circuit is open and hence the circuit breaker is not closed. Okay, so you can see the moving contacts and fixed contacts of this three-phase circuit breaker. Okay, so now if let us assume initially earth fault has occurred, okay, on any one of the phase R by B among any of these three phases, if earth fault has occurred, then definitely the currents in the phase, in any phase, for example, if phase R or Y or B, whatever it may be. Okay, so the current will no longer remain same in the primaries of these CTs. Okay, primaries of the CTs, current will no longer will remain same. So definitely the EMFs induced across the secondaries of the CTs will no longer will remain same, and hence differential current will flow through the pilot wires. Okay, differential current will flow through the pilot wires, and this means the currents that are induced flowing through the pilot wires due to these two CTs, okay, their difference will flow through this earth fault relay, and this phase fault relays will remain inoperative. Okay, if earth fault occurs, only ER will operate. Okay, and the fault currents will flow through this earth fault currents will flow through S1 and S2. Okay, to the neutral current, S1 and S2 to the neutral of the CTs. Okay, S1, S2 are means through the neutral point they will flow towards the ER through this S1 and S2. They will flow towards the ER, and this ER will measure the, see, all the relay CTs are connected to the neutral here. Since all the relay CTs are connected to the neutral, definitely if earth fault occurs, current will flow through these neutrals through S1 and S2 to ER. Okay, so this earth fault will flow through ER, S1, S2 towards this ground, of course. If LG fault has occurred, it has to go to the ground. Okay, so it will flow to the ground, and if this fault current exceeds the preset value, then this ER will be energized and this strip circuit will be closed. Okay. Now, if fault occurs between phases, okay, phase to phase fault occurs, then definitely the currents in the secondary EMFs, currents in the primaries of the CTs will no longer will remain same. Hence, the EMFs induced across the secondaries will no longer will remain same. Since the EMFs induced across the secondaries of the CTs are no longer same, definitely the currents flowing through the parallel wires will no longer be same, and hence the differential current will flow through these phase fault relays. Okay, so when differential current flows through the phase fault relays, definitely these strip circuits are closed, and trip circuit is closed, circuit breaker is open. Okay, so this is the modified differential protection of the generator. Now next one is biased. Sorry. Next one is biased differential protection and percentage differential protection. You can call it as biased differential protection or percentage differential protection. So this is a most commonly used protection scheme for alternator stator winding protection. Okay, so this is the most commonly used protection for alternator stator winding protection. You can call it as biased differential protection or percentage differential protection. Okay, so you can use this protection for face-to-face or face-to-earth fault okay, protection. In this scheme, the CTs, you can see CTs here, okay, on both sides of the windings. Okay, I have shown you circuit breaker here. You can connect outside this, means this whole connection of the CTs, which is not nearby to this winding. It can be placed here. Okay, in front of this CT towards this winding. Okay, you can connect in either way, both are same. Okay, so you can connect the circuit breaker and CTs in this format. Okay, circuit breaker away from this winding. Okay, and CTs nearer to the windings, or you can connect in this way. Okay, both are same. It is not going to affect the operation or protection of these windings. Okay. So here also, in this case also, you can see the CTs are connected in star. Okay, the CTs are connected in star. Their secondaries, if you see, one end of the secondaries are given to the neutral point. Okay, this is our neutral earthing. Okay, their neutral point through and the neutral point of both the CTs is connected by a neutral pilot wire. Okay, neutral point of both the CTs on both sides of all the three phases of the stator winding of the alternator is connected by a neutral pilot wire. Okay, and the other end of the secondaries of the CTs are connected via pilot wires. Okay, so this is our neutral pilot wire, these are the pilot wires. Okay, so of course both are pilot wire, means whether it is neutral or whether it is not neutral, both are same. Whether it is neutral or not, it is same. Simply since it is connected, it's the neutral points are connected by a pilot wire. That's why we have given the name neutral pilot wire. That's all, nothing else. Okay, don't there is no need to confuse between neutral pilot wire and pilot wire. Both are same. Okay, so So if you see here, these pilot wires are connected. The secondaries of one end of the CTs are connected together by a pilot wire, but in between there is a coil known as restraining coil in all the three phases. Okay, restraining coil is there in all the three phases. Okay, so these restraining coils are energized by the secondary connections of the CTs in each phase. Okay, the restraining coils are energized by the secondary coils of the CTs in each phase, and the operating coils OC. You can see here OC is the operating coil. These operating coils are connected at the center tapping of these restraining coils. Okay, operating coils are connected at the center tapping of the restraining coils and the neutral pilot wire. So they are connected in between the neutral pilot wire and the center tapping of the restraining coil. These are the three operating coils for these three phases, and these are the three restraining coils. Okay. So in this method of protection, the currents at two ends of the protected section, okay, are sensed using the CTs. Okay, currents at both ends of the CT of this winding, stator winding is sensed by the CTs. And now let us consider two cases. There is one normal operating condition, and the one is faulty condition. Let us start with the normal operating condition. Now under normal operating condition, when there is no fault in these windings, in the stator windings of the alternator, okay, the currents in the, of course, the currents in the primaries of the CTs in all the three phases will remain same. Since the currents in the primaries of the CTs in all the three phases is same, induced EMFs across the secondaries will also be same, and hence the currents in the pilot wires will be equal and opposite to each other. Okay. So they will be equal and opposite to each other, hence the relay will remain inoperative. Okay. Now, when current in the secondary pilot wires is same, we can say that there is a balanced circulating current in the each phase of the pilot wires. Okay, and the relay restraining wire. Okay, so since the currents in the pilot wires are equal and opposite to each other, we can say that there is a balanced circulating current in the each phase of the pilot wire and the relay restraining coils. Okay. Therefore, no current will flow through these operating coils. Okay. So, since there is no differential current in these operating coils, the relay will not operate. Okay. If the relay will not operate, trip circuit will not be closed. Okay. If the trip circuit is not closed, circuit breaker will remain. Okay. Will remain closed. Circuit breaker will not open. Okay. Now let us assume there is a fault, either LL fault or LG fault here in the stator windings. So whenever there is a fault, definitely differential current has to flow through this operating coil. Okay, differential current will flow through this operating coils of this protected skin. Okay, so you can adjust for. Of course, here three phases are there. So if there was only one phase, I might have told you I1 minus I2 current will flow through the operating coil. But since there are three phases, we have to distinguish between the differential currents if I am using some notation. So I will not use any notations. Okay. So the currents means this. Balanced, there will not be any fault occurs, LG or LL fault occurs, there will no longer be balanced circulating currents in the pilot wires and the relay restraining coils. Okay, so therefore differential current will start to flow through this operating coil. Okay, so when differential current flows through this operating coil, what will happen if that differential current exceeds the preset value of the relay? Then the relay will operate and trip circuit is closed, and hence the circuit breaker is open. Okay, so this is the operation of your biased differential protection, and you can adjust the tripping for certain setting, and restraining can also be adjusted to certain percentage value. Okay, tripping time you can vary, you already know that. Okay, you can set the tripping time of the relay, as well as restraining percentage. Restraining coil percentage can be adjusted with certain value. If we are having an assessment on percentage bias relay in our laboratory. So in that laboratory, you will have more clarity. You will be knowing how to set the percentage bias. Okay. So in our laboratory for different percentage biasing, we will see how the relay operates, how the time of operation of the relay varies. Okay. That we will see. So in this percentage bias relay, we can even we can adjust the certain percentage of the winding. Okay. We can reset percentage, restrain percentage can be adjusted. Okay, so depending on the restraint percentage and time setting of the relay, the time of operation of the operating this operating coil means time of operation. Yeah, of course, time of operation of this relay, as well as the current at which the relay will operate will vary. Okay.